Ladies and gentlemen, my name is Anastasia Chervinska. I represent the team of Russia Voronezh, and today I would like to present you my solution to the problem number 3 in tree. The statement of the problem is here. The drop of the ink is ejected into especially still water, or dropped very close to its surface. So, then it divides into smaller rings. The process repeats, and the tree-like structure of ink is formed. We were asked to estimate the maximum number of ring divisions which can be observed in our system. Here you can see the process of ink tree formation. And this problem is well investigated in literature, so I would like to start with the literature review. The first insight of the problem was made by Thompson, who made a qualitative explanation of the process, and then defined the main physical parameters. Then the group of Horace made a series of papers with experimental investigations of the problem, and I would like to mention the recent paper of Shimokawa, who made the numeric modeling. Our own investigation was began with experimentals with the experiment. We made the experimental setup. We managed to look at the process from the side and from the bottom. So let's come to observation, the main stages of the process. When a drop of ink enters the water, its surface energy converts into the kinetic energy because the ink and water are mixable fluids, so there are no interfacial tensions. Then the ink in the water begins to rotate because of the shear stress on its boundary. Some water begins flowing into the drop and the water ring forms. Here you can see the rotation movement in the drop, and here you can see the vortex ring. We can see that for different Reynolds number, the dynamics is different. If the Reynolds number is too small, the global form, and if it's too big, the droplets break down into the turbulent splash. We managed to find the characteristic Reynolds number for the system by using the solutions of glycerol and water, and thus we can obtain different viscosities. After its formation, the vortex ring expands due to the pressure distribution and decelerates because of the drag force. We can use the conception of hydrodynamic impulse of the ring to investigate quantitatively the motion of the ring. And we write the Newton's second law, use the Kelvin's theorem about circulation, that the circulation can be changed only by dissipated force. And then we can find the dynamics of ring radius and the mass center. We have one fitting coefficient, drag coefficient, and we got quite good agreement of theory with experiment. After that, the ring divides. The division of the ring occurs because of the Rayleigh instability. The density of ink is bigger than the density of water, and because of it, any small perturbations grow exponentially. The Atwood number is quite small, so the fingers are symmetric. We can find the dispersion relation for the instability growth. It's the relation between the growth rate and the wave number by looking at the asymptotics at small wave numbers and at high wave numbers. For long waves, the process is governed by gravity, and for short waves, the dissipation forces are ruling for our process. But also, we should take into account the boundary conditions, because our perimeter of our ring should contain the whole number of waves. So, from this consideration, we can theoretically estimate the mole number, and we can see that there is quite good agreement of theory and experiment for such complicated situation, but their variance is quite big. We decided to investigate the variance, and we got such distribution of mode numbers for fixed droplet trading. We can see that it is close to normal, but the variance is quite big. This is easily explained because an asymmetry leads to the growth of instability. So, finally we get such method of calculation, the realizing mode number in our system. We know the dependence of radius of ring on time, and we know when the ring will divide. So, by knowing the radius at the moment of the division, and we can find out the realized number of nodes. The process of ring formation and division repeats until the diffusion will stop it. We use such a technique to estimate the number of divisions. We can compare the time lag between the division and formation of each ring and the characteristic time of diffusion for this ring. And thus we can get such criteria of division for the stage that the time lag between division and formation should be less than characteristic time of the diffusion. We used the technique proposed in literature to measure the diffusion coefficient. We compared the solution of the equation of diffusion with our experimental data. The dynamics of secondary rings should be taken into account because the secondary rings are too small for the wavelengths of the optimal growth rate should come into it. And so the small rings divides into two parts because the division into two parts corresponds to the maximal growth rate of instability. And to quantify the process of division, we use such criteria. We use the dimensionless ratio between the time of diffusion and the time of growth. If the fragmentation number is higher than critical, the ring will divide, and in other case, the ring will dissolve. For experimental estimation of critical fragmentation number, we used 250 experimental situations. For each situation, we found from the video if the ring divide or diffuse. And in such a way, we obtained such critical fragmentation number. And now we can make the analytical expression for the number of divisions. So for each iteration, we only should compare the critical fragmentation number with fragmentation number for this ring. So finally, we obtain quite simple logarithmic expression for the number of divisions, for the possible number of divisions. To test our model experimentally, we varied the initial volume of drop by varying the nozzles in syringes. Our experimental technique may be, for example, discussed in discussion. And we varied the difference of densities by dissolving in water, and for each iteration we also measured the viscosity and the diffusion coefficient. And finally, we compared the number of divisions calculated from our theory and the number of divisions by experiment. And we can test our model experimentally. On this axis is the experimental number of divisions, and on this axis is the theoretical number of divisions. And really, we get quite good correlation with experiment. Now we can come to the conclusions. The conditions here you can see that we obtained really the number of divisions theoretically and experimentally. Thank you for your attention.
I'm from Poland, from the Warsaw University. I will be proposing the presentation by the Russian team about the problem number, I think, 3. Your presentation was have a lot of advantages. It was prepared from the literature point of view. You have a lot of experiments and fluent and understandable speech and approach, and a lot of analytical theoretical approach. But when you taken into account the diffusion, have you taken into account any kind we want to discuss? Because in the diffusion equation you didn't have any kind of temperature dependencies, and as I understand, you derived your model for for all of the fluid parameters like the viscosity and surface tension and the density. But have you checked if this expression holds for different fluids, for example, ink dissolved in alcohol, or the ink dropped into alcohol and something like that? And we want to discuss also two things. If you have any idea if there are any other parameters that can affect the number of the modes, and how did you process your data from this experimental setup of yours? Okay. Cool.
So then we turn to the discussion in the report from the opponent.
Firstly, I would like to discuss the question about the temperature. Really, I think that it's quite interesting experiment, but there are some problems with it, because changing the temperature of the water, for example, we would change not only the diffusion coefficient, but also the viscosity and the surface tension. So there will be problems with analyzing the results of this experiment, because we won't say we couldn't say distinctly what would be the parameter would be the main parameter that would influence the changes in the results. Would it be the diffusion coefficient, or for example the change in viscosity? And
yes, but have you measured any other fluids that have the same temperature but other viscosities and surface tension?
Yes, also in our experiments we used a combination of glycerol solutions, and as the ink we used the glycerol solution colored with food dye. Such combination allowed us to investigate the dependence on the viscosity, which helped us for example, to obtain the critical Reynolds numbers. Also, we tested for this case our equation for the ring dynamics. But for the combination of glycerol and food dye, the number of divisions is quite small, because the viscosity diminished the number of divisions. So our final experiments were made with a combination of ink and water.
Okay, so all the data inside your presentation was the combination of pure ink and pure water, yes?
Yes, all the final data are the combination of ink and pure water, all the graphics in my presentation. But the Reynolds numbers, which were obtained by using the glycerol solutions.
Yes, but because you mentioned that you made some experiments with different fluids, so the results was still in agreement with the theory of yours?
Yes, it was.
So what?
We calculated for other fluids the equations for the ring dynamics and the mode number for the ring, and the relation was quite good.
So it's a shame that you didn't put the data, because it would broaden your experiment. How did you process your data? Because there was very few, I think, non-uncertainties bars in your data, and
You mean you meant? For
Maybe we
example,
can
this-
change this because it would help, because our presentation doesn't need to be displayed right now.
I'm sorry that there are no error bars on these graphics, but it was in the goals of to better represent the data, because in the case if there were error bars, the chart would be very strong to analyze. But you can see that the error bars of the range of error bars, for example, for this distribution. All the distributions were made for each series of experiment.
Okay, and how did you process your data by hand, or you used some kind of automatization?
For this experiment, we calculated the number of modes by the photos from the bottom view. And by analyzing the ring dynamics, we used special.
Sorry, but yes, the number of drops is very easy to spot. But I want to ring. Oh, okay. So
These graphs these points were made by using the special software for analyzing the dynamics. For video analysis, it was a track.
Okay, thank you. So we now turn to questions from the reviewer. Only technical questions.
For the reporter, I want to ask you that you mentioned that a point of ink may turn into rings, and then it will split into smaller points. So do you think it is really necessary for the point of ink turn into a ring?
Please, can you repeat your question?
Is it really necessary for the point of ink turn into a ring first and then split into smaller points?
This case is for human turbulence flash maybe. This is for higher Reynolds numbers. If, for example, the size of the droplets is too big, or there is big initial velocity. It's for high Reynolds numbers.
Okay. And I also remember that you mentioned the mode number of the droplet. So how do you explain the relationships between the mode number and the splitting behavior of the droplet?
The mode number is determined by the wavelength of instability.
Yeah, of course. But does it have any direct relevances between these two things, the mode number and the splitting?
I don't think that it's.
Okay. For the opponent, I want to ask you that do you have any other better methods to process those data?
Can you repeat this question? Can you repeat?
Do you have any other better methods to process those data?
I don't. Sorry, I
Okay,
don't.
time is up. So we now turn to preparation time.
So ladies and gentlemen, I'm really glad to be here to review this discussion. First, let me review the performance of the reporter. The PowerPoint is very beautiful, I have to say. I really like it. And in your experiment, you mentioned the precise behavior of an ink dot turn into small dots. That means the splitting. And you also analyzed the oscillation of the dot. You mentioned the mode number and discussed it rigorously. And you chose time to express the behavior of the ink dot splitting. But I think maybe you can add the analysis between these parameters and the initial velocity. And also you can consider more parameters. For the
time is
opponent
up,
review.
unfortunately. So thank the reviewer for the speech.
Okay.
And we move on to discussion.
They all did a good job.
Reporter and the opponent.
Oh.
That's nice.
Okay, so let's start the discussion. So, do you have any other questions to ask the reporter?
Yes, we've talked about two others. How do you control the droplet size before it?
Yes, I would like to say it in my presentation. Thank you. Maybe I forgot. We controlled the nozzle diameter, the diameter of the nozzle of the syringe, so we managed to produce the droplet of maximal size, for which the cohesion of it to the nozzle would be equal to its force. And from the balance of forces, we can easily calculate the final volume of the drop. And thus, we could maintain the volume of the droplet by changing the nozzles of the syringes.
If I can, and do you take into account how deep the container must be for this to occur? Because you talked about times and other things, and how about the velocity that changes something?
We used the vessel of approximately 30 centimeters high. So the process of division and stops before the second rings comes to the bottom of the vessel. So our vessel was deep enough for our case.
And I would
So,
like
do you think the division of the ink dot is caused by the tiny turbulation?
I'm sorry.
Turbulence.
For this range of Reynolds numbers that we obtain for the formation of vortex ring, the vortex behavior is quite characteristic. If we have strong turbulence, we would have such picture. And if there would be no turbulence, we will get the such globule. And for our case, there is the transition between the laminar flow and strong turbulence.
Yeah, but I mean the instability of water. Do you think it is? Are there any relevance between the splitting and?
You mean what would be if the water wouldn't be still? Yes.
Yes.
Yes, it is very influenced parameters, and we would wait quite a long time after we pour the water into the vessel until it becomes still enough. Because if the water isn't still, the rings wouldn't be symmetric at all. The process of instability is very sensitive to all of motions around the ring, for example.
have you tried numerically somehow simulate this phenomena? Because most of the equation is there.
Really, the numeric simulation was done by the Shimokawa in quite recent paper, so I didn't like to repeat the obtained results.
Team members are now allowed to join the discussion.
And do you really think that the ink will constantly move downward and not upward?
It's a very interesting case if, for example, we take the salt solution instead of water. If the density of ink will be less than the density of outer liquid. And in this case, the ink droplet will have the initial velocity, then it moves a bit into the water, but then it will grow upward. It's a very beautiful picture for me.
Maybe let's let
Okay,
Timo
okay,
ask
okay.
ask the question.
Yeah.
What is the role of visibility of fluids, and what would happen if the fluids were invisible? This basic formula. What would happen if the fluids were invisible, if they can't mix?
Okay, so we made measurements and just fall without mixing, just fall down into the. We tried, I think, glycerin with acetone, and it didn't mix, and it just
No rings were created.
no, just the drop just fall down into the vessel.
Very rough.
Yes, I also obtained these results. Really, if we take, for example, the oil and water, the rings are possible to formate, but the initial velocity should be quite high, and it's very rare experimental situation. It's almost unrealistic in our experiment.
Okay, so when you mentioned the initial velocity, did you try to, or do you think that the height that you could drop from to the vessel, maybe it will give enough kinetic energy to form these rings? What's your opinion about it?
Yes, it will, but there is quite an interesting influence of the if we want to eject the drop into the water, but if we will pull it from some height. For example, in some cases, something like the air layer between the drop and the water will form, and in this case the situation will slightly change, and in this case the turbulence is quite easy to obtain. Instead of ring, we obtain the splash into a lot of droplets.
Okay, about this temperature measurements,
Not always, but sometimes.
I have because you said that it was very difficult to change to change only temperature, but what would be your prediction? Okay, because we did some changing temperatures, and what would be your prediction if the temperature is higher? Would it be more the springs or?
Yes, of course, it's quite easy to predict, really. If the temperature will be higher, the diffusion coefficient also will be higher, and in this case, the number of division will be less. And by diminishing the temperature, by decreasing the temperature, we can, I think, a bit increase the number of divisions. Yes, I think it will be so.
I remember you have discussed the time as a reality, and you used the second rule. And I may ask you to describe the way the ink points go in a simple way. The way it goes down.
The ink points?
Yes. You take time as a reality. Yes. I'm thinking about that.
You think that you meant that the ink is the colloidal solution? Yes. Or no?
Yes.
Yes, thank you. It's quite an interesting question, but we can calculate the Stokes number for the points of ink into the all of ink, and we can find out that the points of ink will move with the flow.
Yes, well, I've just talked about how it moves, about the height and about the lines.
Okay, thank you. Time is up. So we now move towards the concluding remark by the reporter. You have 1 minute.
So I would like to thank you for your attention. I think that the question of this task is very different and the phenomena. is very beautiful. I hope that you liked the videos. I think they're beautiful. Thank you for your attention.
Can get back up on stage because we now turn to questions from the jury. So there are 6 minutes for that, but I would like for each jury member to just pose one question to begin with, and then if there is more time, then you can ask a second question. So, does anyone want to start? Andreas.
So could you show the slide again with your final expression for
Yes,
the number of rings?
of course.
Yes, and here V naught, that's the initial volume, yes, and delta rho is the density, and T is gravity, and M naught, what is that?
It's the number of divisions for the first iteration. We
Ah.
used all of our technique proposed above to calculate this.
Oh.
My question is also about this formula. There are several parameters. Which ones have a rare change to prove this expression?
The initial volume.
Only volume or something
no.
else?
The initial volume, the difference of densities, and the difference of densities.
Two parameters.
Parameters, but also by we changed the we used such technique to compare our theory with experiment because we changed the difference of densities by dissolving in water, and in this process the diffusion coefficient changed and also the viscosity of the liquid also changed.
And my second question on the same thing. Your expression gives theoretically unlimited value of divisions. Yes, you can take very large volume, for example, but
Yes.
I still ask. And can you give, for example, 100 of divisions or something? Okay.
No, it's just because the Reynolds numbers. The Reynolds numbers gives us the fundamental restriction for the volume of droplet and for its for initial volume of droplet. If the Reynolds numbers are too high, the droplet will be splashed into a big number of little droplets. The ring wouldn't form at all.
So your formula has limitations.
Yes, it has eliminated. It is only for the case when the ring is formed, the initial ring.
Okay, and if so, what is your estimation for the highest value of divisions?
20 or 30. It depends. It depends also on the. 12 or 13. I'm sorry.
12 or 13?
12 or 13. It's for quite. It's for quite strange liquids with very low diffusion coefficient, and we didn't obtain it experimentally.
Did I understand correctly that you consider the division of the ring by using the Rayleigh-Taylor instability approach? Yes. So you consider the surface between ink and water to be flat. It doesn't have the radius of the ring in the formula.
We estimated the modification of the formula for this case, and the modification is quite small.
Is there any particular reason that you don't see in M equals 3 instability breakdown? You have the graph with how many rings
Yes.
will break down. use the first way of using it. Is there any particular reason that it's three?
No,
You don't
no,
have three readings.
No, three. It's just because the number of experiments, I think, because it go.
I have questions for all of members, and please start from Chinese team.
Improve this work.
Yeah, shortly, like one sentence.
Control the water, I think.
What?
Control the water.
Control the what does it mean? Control the water.
Water. That means make it make the container as large as possible.
You mean mechanical thing?
Mechanical. Yeah.
Okay. Thank you.
Measure the predictions with the multiple variable combinations, so we can prove that this formula holds for all the variables combination, not only for the small subset of it.
Thank you. And you?
I think yes, I agree with the point. I think that I would like that I could have the opportunity to take the liquid with a very low diffusion coefficient and to obtain to take the formula for quite large number of divisions, and see the maximum number of divisions obtained in our experiment is only 5, but I would like to test in the range of parameters which give something like 9 or 10.
Thank you.
Okay, that concludes the questions from the jury. I'm sorry I can't continue, but I'll give you the first question next time. So we move towards the jury should decide the marks at 1 minute.
Thank you.
And I will remind you, since it's the first round, to try to make sure that you will still be able to use the full range for the rest of the tournament. Okay, are you all ready? Good. Then we start by showing the grades for the reporter. So we have an 8, 8, 8, 7, 9, and an 8. Thank you. So a 5, a 5, 5, 5, 5, and